This problem presents us with 3 blocks of mass, each attached by strings to a surface where they are all 3 hanging in equilibrium, and it says solve for the force of tension between mass 1 and mass 2. So it's force of tension in that string where mass 1 is equal to 20 kilograms, mass 2 is equal to 10 kilograms, mass 3 is equal to 5 kilograms. So first, let's follow our checklist. First, create a free body diagram labeled. So let's create, because we can't get forces of tension between 2 specific ones of them using the system method, because using the system method, we can't use the system method, so we have to use the object method. So we have our M1, M2, M3. We need all 3 of them. So the forces acting on each of these individual ones. Okay, I'm first going to start with the ones that would be easiest. And the easiest one is going to be M3 because all that has with it is just this one string instead of having 2 strings. So first, we're going to do a force of gravity down because on our checklist it says that force of gravity is always straight down. So we have force of gravity straight down. Keep this here. Force of gravity on mass 3. And then we have a tension force between mass 2 and 3. Force of tension 2 to 3 going up. Now we know that which direction this goes, whether it goes from 3 to 2 or 2 to 3 or 2 to 1 or 1 to 2, doesn't matter because they're equal to one another because of the fact that it's hanging in equilibrium. If it wasn't equal, they would stretch the strings, or the strings would compress, or they would just fall. And that's not the case. So now we also know that our M2 is the tension that goes downwards from FT2 to 3. Also, it's force of gravity in 2. And then we have a tension that goes upwards as well, force of tension 1 to 2. And then our 1 has a force of tension in the 1. So I'm going to go like this as well. It has a force of tension in the 1 that goes upwards. It has a force of gravity. I'm going to move this one over. I'm going to make a bigger dot here. It has a force of gravity 1, and then a force of tension that goes from 1 to 2. Okay? And this force tension here goes between 1 and the ceiling, so I'm not going to write 1 through ceiling. I'm just going to write force tension 1. So, in other words, what we're trying to solve for here is force of tension 1 to 2. That's just a quick way to put it because of what we set up here. Now, we can solve for things. We can first set by this, it says set axes in positive and negatives and split necessary forces into x and y directions. So we have our positives that we'll say we're going up and to the right, and the negatives that we say we're going down and to the left, although our right and lefts do not matter because there aren't any right and lefts, there's only up and down. So let's set everything equal to positives and negatives. Positive and 2 negatives. Positive, 2 negatives, positive, and only 1 negative. So first, let's do this. We have our M1. Sum of the forces on 1 is equal to force of tension 1, because that's our positive, so this one stays positive, minus force of gravity 1, minus force of tension 1 through 2, because that would be our sum of forces. We also know that because this is not moving, our M of A is equal to 0, so we can just go like this with it and go 0. Now I'm going to move this over here because I can. I'm going to keep it up right now. You guys can barely see it. Cool. Now our force on number 2 is equal to 0, but I'm not going to write it yet because I want to make it even and look all nice. Force of tension 1 through 2. Hey, there's something we actually need to figure out. And so is that one. Minus force of gravity 2, because that's negative, minus force of tension 2 through 3, because that's also negative. And that's equal to 0, because our mass acceleration is 0, so all of it's 0. Now, our sum of forces in 3 is equal to force tension 2 to 3 minus force gravity 3, and it's also equal to 0. Okay, literally just the same thing 3 times, except this one doesn't have an extra force of tension because there isn't a rope on the bottom of it. Oh, great. So now, let us solve for things. First, we're going to go to the simplest one, the one that doesn't have as many components, is our 3. Now, first what we're going to do for the 3 is we're going to rearrange this equation to make a bit more sense. Ft2 3 is equal to Fg3. I got to this by just adding over this negative Fg3 to the 0, and then you get this. Now, let's solve for things. Our thing over here, force of tension from 2 to 3 is equal to our force of gravity on 3. Our force of gravity on 3 is equal to mass 3 times our gravity. Our gravity is always 10, so now if we were to actually solve for what this equals, our force of tension, I like to do the derivations in red and then do the actual work in black. So force of tension 2 through 3 is equal to mass 3, 5 kilograms, times gravity, which is 10. Okay. Our force of tension 2 through 3 is equal to 50 newtons. Okay. Now let's do that same exact thing, but for this one now. Now, we can't use this one for that because we just solved for this here. And this here is only applicable in this one. There's only this here. There isn't a force of tension 2 through 3 in this equation. So now let's just add over the subtracted things. So we have a force of tension 1 through 2 is equal to force of gravity 2 minus force of tension 2 through 3. Oh, not minus, plus. Can't forget that plus sign. Now, what we do is, this is our equation, so let's derive it a bit further, and also get this isolated. So we have, let's subtract this over, so instead we're going to do this, which is equal to the same thing. All I did was subtract this back over. So now we have force of tension 1 through 2 minus mass 2 and then gravity is equal to force of tension 2 through 3, which is what we were looking for. Oh, no, it's not what we were looking for. We were looking for 1 through 2, so I don't actually want to do this. Always refer back to what we're doing. I didn't and paid the price for it. Okay? We weren't solving for this. I am dumb. Okay, so now let's plug back things in. I didn't say that right. Plug things back in. Force of tension 1 through 2. It's late, okay? Give me a break. 10. Gravity is always 10. Plus our force of tension 2, 3, which we already said was 50. Force of tension 1 through 2. This is 100. 100 plus 50 is equal to 150 newtons. And that is what we were looking for. Now, under the situation where this would ask for what's also the tension between M1 and the ceiling, there's 2 ways we can go about it. Because M1 in the ceiling would be the entire system's weight, because if you notice how, like, progressively it's like, oh, this stacks onto this, and then this stacks onto this, and how that whole process plays out, it's the same thing as just doing the system, but for just this part. But we're going to do the full-fledged way because we also wanted to figure out Ft1 minus, or 1 through 2. Tension between 1 and 2. That's the words. Now, if we wanted to do the whole thing, though, from this, we would say, let's do Ft1 is equal to Fg1 plus ft1 through 2. If you don't know how I got there, where have you been? And so ft1, let's simplify it back down. We have a mass 1 gravity because that's what ft is equal to. We already said ft, we're not going to do that just yet because I want to do all derivations like that. Now, let us do plugging things back in. ft1 is equal to mass 1 is 20 kilograms times gravity, which is 10, plus our ft1 which is 150. Our ft1 is equal to 200 plus 150 is 350 newtons. Now, I'm gonna go little cloud. And then just food for thought, if we wanted to figure out only this tension from the get-go, we could actually do the system method and then just go like this and then do mass of the system, which is literally just all three of them added up. So if we wanted to do that, if I wanted to create a free body diagram that would represent that, I would go like this, and we have a tension that goes upwards, tension, force of tension over the system, and then we have a force of gravity over the system. And then set our positives and negatives. We have it already up here. This is a positive, this is a negative. Make our equation. Our equation looks like this. Force over the system, sum of forces is equal to 0 because it's unmoving, which is also equal to force of tension system minus force of gravity over the system. So if we solve for this, we would get Ft system is equal to, and then I'm going to do two steps at once. Not only am I going to get this into the form I did here, or here, this would be probably a more accurate one, but I'm going to do this step all at once. So I'm going to go from here to there. M system gravity. If you want to see how I did that, just review this. And then force, oh, I'm not going to do this here because wrong color. Force of tension over the system is equal to mass of the system, which is 20 plus 10 plus 5, because that's all of the mass. Gravity is 10. And then now, force of tension over the system is equal to 20 plus 10 plus 5 is 35 times 10, 350 newtons. And that's exactly what we got here. So if you're looking for a normal force or a tension of just this one, where it's just the connecting between the surface and the first mass in a chain of masses, it is better to use the system method because that will get you an answer in a shorter amount of time, and time is of the essence on tests, especially AP tests. But if you're looking for a specific force of tension between two of the individual objects, you need to go the long route. Yes, it's annoying. Yes, it sucks, but that's what you got to do. And that's this portion.